Welcome back to real time digital signal processing course. So, last class we discussed about the discrete Fourier transform. In this today's class we will see the complexity of filtering and then how FFT is going to be derived. So, what is how we represent our digital filtering? We know that the equation for our FIR filter, for a simplicity what we will take it here. So, x of n is our input and h of n is our h of n be real signals, that is two signals if we want to take it, or the impulse response of the filter, what we will consider it as h of n. So, if we assume the coefficients, it becomes b of n in FIR filter. So, x of n is we are representing it as 0 to n minus 1. Then we have to compute our y of n using the as we can see here the star indicates the linear convolution. So, how we can represent? K will be varying between minus infinity to infinity, x of k into h of n minus k, or we can represent k is equal to 0 to n minus 1, because this is what our length of sequence, input sequence. Then what we will show is x of k into h of n minus k, or we can, as you know that since this is a LTI system, so we can have x of n minus k for my x and then h of k for my coefficients, what we have seen in our DSP implementation. So, both the ways are correct. Here we will be assuming at present to derive x of k into h of n minus k. So, what is it? So, we have to say that what is the complexity of computation of this linear convolution. To make it simpler, instead of convolution we will assume it as a multiplication at present. K will be varying between 0 to n minus 1 and then x of k into h of n minus k. So, how many real multiplications I am going to do it, because it is 0 to n minus 1, n real multiplications, and with x of k into h of n minus k, and then we have to have the summation, which is going to be 1 less, we will be assuming it n minus 1 real additions are required for all n varying between 0 to n minus 1. Then if we assume that my n is also length of 0 to n minus 1, then total number of multiplications for our filtering required is n into n, that is n squared. We say order of n squared real multiplications are required, and then addition we know n into n minus 1 additions, which is nothing but this also results in order of n squared real additions. So, total number of multiplications and additions are required is order of n squared, which we consider it as very high. Okay. So, how we can do filtering in the frequency domain, which can reduce our complexity, what we will be looking in a few slides. So, what is it? We will say discrete Fourier transform, we say it is a frequency analysis of discrete time signal. It is how we can perform it on the DSP, that is what we will be looking at. So, both time domain and frequency domain the signals must be in the discrete format. So, x of t is our analog input, after sampling I will be getting x of n in the digital domain, and x of omega, which is omega is continuous, after sampling it we will be getting x of 2 pi k by n, or we call it as x of k. So, we will be representing 2 pi k by n as k in this case, that is capital K. So, we will be seeing some of the duality of the Fourier's domain thing. One is in the time domain, what it is represented in the frequency domain. If it is a sinc function in time domain, which is going to be rectangle in frequency domain. So, if it is rectangle in our this thing time domain, it becomes a sinc function in our frequency domain. So, if I think some of you would have heard sinc squared function, it becomes triangle in frequency domain, vice versa. And we will be seeing that it becomes a ringing in case of time domain, then it becomes a truncation in the frequency. So, the other way around. So, if it is discrete in time domain, which becomes periodic in our frequency domain, and if the input signal is periodic, then it becomes discrete in our frequency domain. So, if it is continuous, it becomes aperiodic in frequency, and if it is aperiodic in time domain, it will be continuous, and then you can have many more like this in the duality what you can consider. So, few of it which is required for our derivation, what we will be using it here. So, coming to DFT. So, we know that if the signal is aperiodic plus discrete in time domain, then if I take the Fourier transform of this, so that means to say if x of n is aperiodic and my h of n is discrete in time domain, what I will be getting, the result is continuous time signal in Fourier domain plus periodic in frequency, what I will get it. So, by doing the sampling, I can reach this discrete signal what I can get plus periodic in frequency what I can achieve from this stage, or I can have a periodic signal in the time domain plus DST in this thing discrete time signal here, then I can get discrete plus periodic in frequency when I do the Fourier transform. Or if the signal is periodic plus discrete, then if I take the discrete time Fourier series, basically if I convert it, then the output is going to be periodic plus discrete. So, we will be seeing that one period of our discrete sample DFT, I will be getting one period of discrete samples here. So, here n is equal to 0 to n minus 1. In this case, we will be having k will be varying between 0 to n minus 1. So, now how to represent it both in time and frequency domain relation, what it is shown here. So, you will be seeing that this is a periodic plus discrete time sample what it is taken in the time domain. So, you are seeing that this is my x of n, and then now when I take the DFT, so I will be getting x of k here. If I take the discrete time Fourier series, then what you will be seeing is periodic plus discrete in this thing time domain. So, this is how the samples have been represented in that. So, this will be x axis will be k, and then our y axis will be representing periodic plus DST in frequency domain. So, coming with the thing how we are going to do the frequency domain sampling, what we are going to achieve. So, that is we have already said sampling in time domain, we said it is going to result in periodic repetition in frequency. So, when I represent x of n, so we say that it is a repetition of it x a of t, we represent t is equal to n t, then take the Fourier transform, we result in x of omega, which is nothing but 1 by t into k sigma, k is equal to minus infinity to infinity. This is the this thing periodic signal x a into omega plus 2 pi by t into k. So, similarly sampling in frequency results in periodic repetition in time. What we will be seeing it, that is this is the periodic signal what we are representing as xp of n in the time domain. Then it is going to result I is equal to minus infinity to infinity x of n plus I n, and then I will be taking the Fourier transform which is equivalent to x of k, which is nothing but x of omega. In this case omega is represented by 2 pi by n into k. So, now we will see the thing how the sampling is going to happen. So, we know that n is proportional to omega, that is sampling rate. So, that is n samples per 2 pi what we are going to have it in this region is the 0 to 2 pi we will have n samples. So, we know that x of n when we take the Fourier transform we will be getting x of omega. So, the periodic representation xp of n if we take it, Fourier transform, we will be getting x of k in this case. So, we are seeing that is samples of x of omega used in the reconstruction of xp of n, and from xp of n we can get x of n can be reconstructed in this fashion. So, we will be seeing that this is what we are varying 0 to n minus 1, next one will be the n sample, k is going here, and this is our omega x axis. So, here it is you are seeing when n is equal to 2 pi, this is the axis, and then n minus 1 point will be 2 pi minus 2 pi by n. So, this is the resolution what we will be calling depending on our n samples. So, coming to the how we can do the reconstruction, because we have gone from time domain to frequency domain, but my output I want it in the time domain. So, how we can do the reconstruction? So, this is shown with n is equal to 4 in this case. So, you can see that this is my x of n which has 4 samples. The magnitude you will be seeing that this is 0, 1, 0, 1 what you have taken, rest of them are zeros, both the sides negative and then positive side. This is my n basically, and then we will see that we are assuming because I have n is equal to 4. So, we do not have any temporal aliasing in this case. So, this is my x of n basically, this is the periodicity what I have taken. So, you will be seeing that the magnitude at x is 0 it is 2, and then x is equal to 1 it is 1, and then x is equal to 2 it is 0, and then this is 1. So, you will be replicating them on both the sides as you can see it. So, these 4 samples you will be seeing that it becomes 2, 1, 0, 1, 2 again. So, on the negative axis also what you will be doing the repetition. So, we do not have any aliasing because they are distinct in nature. So, you will be seeing that x of n is a unit step response, all of them are 1. Then what happens in the time domain? So, we said that if it is a rectangular window, it should result in your sinc function. So, here you can see that what is the happening is in the periodic, if I take the thing, then you will be seeing that these two are 1s, and then that is magnitude is 2 and then 1, and then which is not equivalent to my x of n. So, the sampling rate if you have n is equal to 4 you have kept it, but x of n is what you have given more than n. So, I will not be able to reconstruct the signal. So, you are seeing that aliasing happening instead of 1 magnitude of what I have supposed to get it. So, 2 of the samples which have got aliased and then which has gone to peak magnitude 2 in this case. So, what is sampling and then reconstruction, how they are related in the frequency domain, we will see it. So, x of n can be recovered from our periodic xp of n if there is no overlap when taking the periodic repetition. So, if x of n is finite duration and then non-zero in the interval 0 to L minus 1, then what we say is x of n is equal to xp of n in this domain 0 to n minus 1 when n is greater than or equal to L. So, if it is less than, then we know that aliasing is going to happen for the periodic signal. So, if n is less than L, that is what it says, cannot be recovered from our periodic xp of n. Also, x of omega cannot be recovered from its samples, that is x of 2 pi by n into k, due to time domain aliasing what has happened. As the previous slide shows that what was the initial thing, but here all of them are 1. So, we are not getting back in this case. Okay. So, now what is the relation between our DTFT, DTFS and then DFT? So, x of n for all n, if I take the DTFT, then it becomes x of omega for all omega, and then the periodic signal in the time domain xp of n for all n, and if you take a discrete time Fourier series, then it is going to become x of k for all k. So, we say that x tilde of n, that is periodic DFT, if I take it results in the periodic x of k. So, here x of n periodic what we are represented instead of xp of n. So, for n is equal to 0 to n minus 1, it will be 0 otherwise, and then what happens in the frequency domain, x hat of k will be x of k in this 0 to n minus 1, other thing is 0. So, what are the, we have seen the DTFT pair. So, now we will see the DFT pair. So, that is we have taken the example and we took the IDFT. So, we call them as pair. So, this is the analysis function and this is the synthesis what we call it, that is capital X of k is given by n is equal to 0 to n minus 1, x of n into e power minus j 2 pi by n into k or k n by n whatever way you represent it, k will be varying between 0 to n minus 1. The inverse what we have seen it is x of n is nothing but 1 by n. So, k is equal to 0 to n minus 1, x of k into e power same thing, instead of negative here it becomes positive. In this case n will be varying between 0 to n minus 1. So, what is the complexity of DFT, what we have seen the thing. So, with respect to our signal processing hardware, we will see what is the complexity of our DFT. Complexity of filter, what we have seen the thing, we have to see the complexity of our Fourier transform, the discrete Fourier transform. N is equal to 0 to n minus 1. So, we know that x of into w n k n, k will be varying between 0 to n minus 1. So, we know that straightforward implementation of DFT to compute x of k for k is equal to 0 to n minus 1 requires, just like our filter order of n squared, here it is not real multiplications, it is going to be complex multiplications, because x of n has to be multiplied with cos and x of n has to be separately multiplied with our sine, which is imaginary part, and they have kept separately. So, that is why it needs complex multiplications in this case, and then we need one complex multiplication is equivalent to what we call it as AR plus JAI into BR plus JBI. If I do it, this is what I am doing. So, both xn and then my coefficients are we call it as complex, xn is also complex, we have assumed. When we do this multiplication, you will be seeing that it is nothing but AR into BR minus AI into BI plus J times AR into BI plus AI into BR. So, what does it show? 1, 2, 3 and then 4 real multiplications. So, one complex multiplication is equivalent to 4 multiplication plus I have to have, even we take it as subtraction as addition, because we do in 2's complement if you call back your number system. So, we have 2 additions, real additions. So, what happens to our total computation time, which is equivalent to 4 into n squared, which is nothing but order of n square real multiplications what we needed. So, which is same as that of our filtering. So, we will see that how we can reduce or take that forward. So, in this case we said only multiplication we covered the thing. Now, we have to see from the addition point of view. So, what is it? Our filtering was needing n into n minus 1 real time additions, but in this case it is going to be n into n minus 1 complex additions. How do we represent one complex addition? That is AR plus JI. This is what we say is plus BR plus JBI. So, this is my equation AR plus JAI plus BR plus JBI. So, it will be AR plus BR plus j times ai plus bi. So, that is how we will be resulting in two real additions. And then when I want to do the total complex multiplication, and then we take that 2n into n minus 1. So, we will be deriving it once again when we take up the problem. So, it will be coming it as 2n into n minus 1 plus 2n squared, that is which is arriving from my complex multiplication. So, some of the additions taken from there. So, this many number of what I need is real additions. So, what does it mean? So, this is the complex addition. So, 2 times, because each complex multiplication we are taking it as 2 real addition. So, which results in 2 into n minus 1 from this stage, and then we know that from the complex multiplication we have addition which is resulting. So, which comes to 2n squared. So, that is what it is rendered. From complex multiplication I have to take this also into account. So, this is what our total number of additions required for computing my DFT. So, in that case the maximum is 2n into n minus 1 if I take it, if we absorb this also inside. So, additions also what we need is order of n squared. That is the complexity of DFT. Both real multiplication and real additions are order of n squared. So, we know that already we have pointed out in the filtering, it is too high. So, linear increase in the length of the DFT increases the complexity by a power of 2 basically. And if you are given the this thing, what is it, multitude of applications, that is number of them where Fourier analysis is employed, that is we will call it as linear filtering or correlation analysis, which we will be taking it up little later, and then do the spectral analysis, what are the intention of our applications. Then we will say that how many this thing, what is the complexity of it, that is efficient computation is required. So, that is reduce the complexity by exploring the symmetry property of our complex exponential. So, how we can do that? We have that Twiddle factor, we saw that W n k plus n by 2 is equivalent to minus W n k. So, we will see the left hand side is nothing but W n k plus n by 2 is equal to e power minus j 2 pi, substituting k with k plus n by 2, k plus n by 2 by n, which is nothing but e power minus j 2 pi k by n into e power minus j 2 pi n by 2 by n. So, this results in minus 1, that is what is shown here, e power minus j 2 pi k by n into e power minus j pi, which is nothing but this cos minus pi plus j sin minus pi when we expand e power minus j pi, and then we know that cos minus pi is minus 1 and sin pi is going to be 0, pi or minus pi is 0. So, which will be minus 1. So, when we represent this is nothing but minus n k. So, that is how the derivation between the two has been arrived at. So, LHS is equal to RHS. So, whatever we are representing, that is symmetry property is true. So, now how we can extend this? Usually we call it as decimation in time basically, that is x of k is equal to n is equal to 0 to n minus 1 x of n W n k, and this is our normal DFT equation, k will be varying between 0 to n minus 1. So, now what happens? So, if n is even, then n is equal to 0, what we will be taking it x of n plus W n k plus, that is we are considering even and then odd parts. Next n is odd, x of n W n k. So, here it is going to be, we are changing the little bit of notation from n, actually m is equal to 0 to n by 2 minus 1. x of 2m because it is a even, and Wn k times 2m, n is substituted with m in this case, and this is our art part. M is equal to 0 to n by 2 minus 1 x of 2m plus 1 Wn k times 2m plus 1. So, this is how we can split our DFT equation into even and then odd parts. So, when you can see that we represent x of 2m as f1 of m, and we are seeing that this has become already Wn 2km, and then this we call x of 2m plus 1 as f2 of m equivalent to, and then this is Wn 2km into Wnk. So, we are going to split like this decimation in time, and then we know that Wn2 is nothing but by substituting k is equal to 2 e power minus j 2 pi by n into 2. So, which is nothing but e power minus j 2 pi by n by 2, what I can take it. So, the twiddle factor, it is going to be Wn by 2. So, then we will represent x of k is equal to what we have is f1m and then f2m. So, by substituting this f1 of m, and then we are substituting our Wn2 actually with respect to this, it becomes Wn by 2 into km, plus we know that Wnk is independent of n. So, which we will be taking it out Wnk, and this is our sigma for the f2 of m Wn by 2 into km. So, you will be seeing that this is n by 2 DFT of f2 of m, that is what we have it. Then if we represent this as this is n by 2 DFT of f1 of m, if we substitute that as capital F1 of k, plus this is going to be Wnk f2 of k. K will be varying between 0 to n minus 1, and then we know that f1k and f2k are n by 2 DFTs. So, you will be seeing that f1 of k plus n by 2 and f2 of k plus n by 2, and x of k is going to be that is DFT of it will be f1 of k plus Wnk into f2 of k. So, now what we are going to represent that k also will be taking the symmetry property, we will do it as k plus n by 2. So, we can have it as f2 k plus n by 2 plus Wn k plus n by 2 into f2 of k plus n by 2. So, here it is f1 of k plus n by 2 plus Wn k plus n by 2 into f2 of k plus n by 2. So, which is nothing but f1 of k minus Wnk into f2 of k. So, how this has come? You will be seeing that Wn k plus n by 2, what we have to solve the thing, which is nothing but e power minus j 2 pi by n k plus n by 2, which you solve the thing. So, which is nothing but e power minus j 2 pi by n into k into minus 1. So, this is our Wnk. So, you can see that k plus n by 2 results in Wnk. So, we can split this decimation in time further. So, that is x of k is nothing but f1 of k plus Wnk f2 of k. K also will be going between 0 to 1 to n by 2 minus 1, and then x of k plus n by 2 is given by this equation as we have already computed, minus Wnk into f2 of k 0 to n by 2 minus 1. Now, this is what we call it as radix 2 FFT, that is in decimation in time what is happening step by step till we go up to last stage is 2. So, you will be seeing that repeating decimation in time f1 of n and f2 of n. So, we will be obtaining f1 of 2n and f1 of 2n plus 1, we call it as v11 and v12. So, you will be going n is equal to 0 to n by 4 minus 1 next stage, and then v21 of n is nothing but f2 of 2n and then f2 of 2n plus 1. So, which will be going by n by 4 minus 1 when k is equal to divided by 2 further. So, that is how you will be continuously going on splitting the thing, that is f1 of k is nothing but v11 of k plus wn by 2 k v12 of k. So, which is going between this, then f1 of k plus n by 4 if you take the thing, this is what you will be resulted, and then that is the next f2 what is split into this. So, which has n by 4 DFTs in this case. How we can represent in decimation in time? This is my for n is equal to 8, it is a simple one to consider, we have considered it. So, the first one is x of 0, the next value is what we need is x of 4. So, we will be doing the 2-point DFT, and then x of 2 and x of 6 we will be doing the 2-point DFT, which is going to be combined with 2-point DFTs here, and then the other two odd part what you can see it x1 of 5, x1 of 1 and x of 5, x of 3 and x of 7 other 2-point DFT what you can do it, and then combine them, and then finally you will be combining as a 4-point DFT. So, you will be getting output as x of 0 to x of 7. So, you can see that input is bit reversed what we have considered in the number system and DSP architecture. We said we need input in the bit reversed format, output will be in order. So, we have seen the example how to generate the bit reversed also using hardware adder. So, when we represent this as the from the previous thing in terms of what we call it as, this is the butterfly structure. So, this is my x of 0 and x of 4. So, this will be my weight W80 and this is my minus WNK what we have it here, it is going to be minus 1, and then we will be combining these two and which goes to the stage 2. This is stage 1, this is stage 2, this is stage 3 where all the things are combined, whereas in the second stage my twiddle factors what I need is W80 and W82. So, in both the cases, and we know that W80 is 1, okay. I have to compute only this twiddle factors W82, whereas in the last stage we need 3 twiddle factors, that is W81, W82 and W83 has to be computed, and then as usual W80 is 1. So, we will be getting the output in order. So, to do FFT computation for n is equal to 8, we know that log 2 of n 8 is nothing but 3, we need 3 stages. So, we will be seeing that how we are going to reduce the thing computation. So, we will be seeing that with respect to this what we have given computational efficiency of n point FFT we will see it. We know that it is n squared complex multiplication and addition what we needed, and FFT we need n by 2 log 2 n. So, we said that for 8 point it was 3 stages. So, if it is n point then we need log 2 n, and we can use the symmetry property, it is going to be n by 2 complex multiplications what we needed using FFT. So, you will be seeing some n points and then what is the DFT multiplication and FFT multiplications with respect to n. So, if it is 256 we see that 65,536, here what we need is 1024. So, FFT efficiency we compute it as 64:1 for our DFT. So, as and when our n point increases, so you will be seeing that computation of DFT increasing very much, and then FFT you will be seeing low, and you will be seeing that 683:1 is the ratio for 4096. So, this is how we do the computation of FFT. So, in the next class we will be seeing quantization of FFT, how it is going to affect our word length, and then even the coefficient has to be quantized. So, number of stages is going to increase. So, it is a pipeline structure what we are going to have it. So, we will see what are the quantization effects in FFT in the next class. Thank you.